Okay, you can hear me? All right. So I would like to thank the organizers for inviting me to the beautiful city of Pecs. I hope I pronounce it decently. So I'm coming from Prague. Just a brief introduction about my place of work. I'm currently working at the first faculty of medicine at Charles University, but I was for 6 years in the IBT, Institute of Biotechnology. Both of these the labs that I was part of are housed in BioCEF, which is institute in the just outside the city limits of Prague. The idea about this BioCEF is that labs from different institutes of the Academy of Sciences and the Charles University are housed there instead of their parent buildings, and this is to help to share equipment and also to foster collaborations between the different labs there. So since Tatiana did a nice introduction about the computational chemistry in general and how we use it for time-resolved calculations, I will. It was very broad, but I will try to, in my case, I will narrow it down to resonance Raman calculations. And I think it's useful to show the typical experimental setup for stimulated Raman experiments. We have first the actinic pump photoexcites our sample, and then after a given time delay, the Raman pump and the probe interrogate the instantaneous molecular structure. And this is detected afterwards in the detector here as a division between Raman pump on and a Raman pump of laser shots. So this is the experimental setup, and from my for the results point of view, I will focus mainly on FMN, and it's a simpler analog here, the lumiflavin. Yes, most of the results are either unpublished or at the preprint stage. I will try to intersperse my talk a little bit with some examples. Here's the first example will be the off resonance of orange carotenoid protein. And then I will briefly talk about the computational concept and the resonance window, about how to calculate the resonance Raman spectra. And I will give an example of FMN embedded in the EL2 lab domain. Then I will talk about the challenge that is presented by trying to compute the resonance Raman intensities, which leads to the benchmark study of lumiflavin. Finally, a comparison of off-resonance, pre-resonance, and resonance Raman spectra on the triple state of lumiflavin, and how calculations can help us to nuance spectral shifts between single and triple states in flavins. First, the first example is the off-resonance part, which is done in collaboration with Miroslav Klos from Eli Beamlines, which is also another institute on, just outside the city limits of Prague. So here is shown the OCP in its resting state. It has a chromophore, carotenoid chromophore between the N and C terminal domains here, which is anchored at these two residues here. It can sense high energy light via its carotenoid chromophore here, and then domain separation happens in its photoprotective state here. Excitation to a hot state happens within femtoseconds, and internal conversion to the dark state here. Especially for a hine-non, we have an intermolecular charge transfer state with a lifetime of 3 picoseconds. And there is another species which is currently uncharacterized. At 34 picoseconds, it can be either independent excited state, a local S1 minimum, or a non-equilibrated ground state. And here is where I will focus on my next slide. So here is the chromophore itself. Some key bonds and dihedral angles here. These values are from the calculation. Recently, paper dealing with the de-excitation pathway suggested via dynamics simulations using a semi-empirical potential that the hop from the S1 to the S0 state happens at about 90 degrees of this dihedral angle here, so there is a rotation around that bond. So we have a rotation from 180 degrees. Here is the computed value down to 0. For the ds dihedral here, it goes up to 200, while the ds prime on the other side stays mostly stable from the starting to the hop to the end product here. So I took this, I ran a short molecular dynamics simulation, and since the species is at 34 picoseconds, so there is no domain separation happening at that short time. I carved out a large cluster, including the whole chromophore out of it, and did molecular relaxed scan of the dihedral angle, of this DD dihedral angle. So everything all other degrees of freedom were led to relax, except those green atoms here, which are anchored to the MD simulation positions, and the scan of the DD dihedral angle stepwise, so by increments of 10 degrees here. So you get energy profile for the ground state. You can see there is a rotational barrier here at about 70 degrees, and you can also, and the product here at about 16 degrees, the non-equilibrated ground state. You can project those values also to the excited states, so we can see the S1 and S2 states here. The values of the other two dihedrals are, for the ds prime is more or less stable, as we can see, and the ds goes up to 200 degrees, more than 200 degrees. So from we can also see that the closest points between the potential energy surfaces is rather close here on the S2 to S1, which means that the DD is kind of the main degree of freedom that lets that connects the hop from the S2 to the S1. While from the S1 to the S0, probably another degree of freedom is required, and you can try and do, instead of this 1 degree scan, you can do 2D or multidimensional scans to find out which are the important parameters. The rotational barriers is quite high in the ground state, but much smaller in the excited states here. And finally, we can, for each of those points, we can compute a Raman spectrum. Here we can see that as we progress, there is a red shift of the main bands. Experimentally, we can also see with this from a linear experiment. From 1 to 10 picoseconds, we can see that there are red shifts of those bands, while at higher delays here, there is a slight blue shift of the main band. Here's the experimental curve again, and we can overlay on it our calculations. These are different spectra constructed from the Raman spectrum here of this point, for example, at 110 degrees, and we subtract the ground state signal so as to simulate the bleach of the experiment. So we can get these different spectra for each one of those points. So here is right at the transition state. We can see the red shift of the band, and here is that non-equilibrated ground state. We can see the slight blue shift. So it seems that these results are more or less matching both what the previous study showed with the semi-empirical potential, but also they match the quite okay the experimental Raman spectra. So it's an indication that this species that has a lifetime at around 34 picoseconds could be could be on the ground state potential energy surface, but not equilibrated. Now, to go briefly through the computational concept, after the photoexcitation, we have the creation of a hole and an electron in our excited state, which creates new unique properties to the excited state. This, after giving enough time for the nuclei to respond to these electronic changes, are translated to structural changes. For example, bond order increase or decrease. And these also translate to frequency changes, so shifts. These are guided, let's say, for a given bond. These are guided by the Hooke's law, which says that the frequency is directly connected to the force constant or the bond strength. Therefore, a bond order increase, for example, for these blue bonds here, will increase the frequency, so you would see a blue shift. Of course, for conjugated systems like this, it's kind of a more mixed picture. Oh, sorry. And specifically for in resonance conditions, there is also another relation here. The intensities of the peaks are depending on the interaction between the reference or the populated state and the resonance state of the transition that is within the resonance window. These are guided also by the Albrecht term, which includes Frank-Condon terms and transition dipole moments here. So vibrational shifts are guided by the structural changes, which in turn are due to whole electron interactions. And within, if we are in resonance conditions, the intensities of the peaks are also dependent on the reference or populated state interactions with the resonance state. Now, when I will talk about the resonance window, or when we are under resonance, most of the experimental results have been done by Aditya, Gustavo, and Yinglang from IBT. The transient absorption, this is experimental transient absorption, gives us a wealth of information about the states that are involved in the photocycle. Here, normally you do a global analysis of the raw spectroscopic data, and this yield evolution-associated spectra, which can be assigned to specific species. So here, for example, the blue line is the equilibrated first excited state of FMN, and the green line is the equilibrated triplet state. The resonance window is guided by the Raman pump, which is for this experiments at 800, and all following experiments at tuned at 800 nanometers. We can see that the lighter color is like the pre-resonance region, and we can see both singlet-singlet and triplet-triplet transitions within that window. So this resonance window is about 0.5 eV. What the calculations can tell us is pinpoint the exact states that are within the resonance window. For example, for this level of theory, we can see that one of the states that fulfill the criteria of being within here is the S7 state. Typically, we calculate then the resonance Raman spectrum of that at the 0-0 transition after computing the 0-point energies. And in this case, these both are pi to pi star states with respect to the ground state. And the difference is that the hole, or where the electron comes from on the higher energy state, is more bonding. That's why it's higher in energy. After intersystem crossing via n pi star states, which are, I'm not going to cover that part. And now the T1 state is reached in the photocycle. And here also, similarly, we can look for states within the resonance window. So from this study here, we can go and calculate the resonance Raman spectra, which I will show a bit later. So here is an example about the resonance enhancement. I picked EL222, which has it's a love domain which has the FMN embedded in the structure. The grade part of the photocycle is common with the free lumiflavin or FMN. You reach the T1 state here. However, in EL222, the photocycle branch is on because we have a conserved substrate here, which forms a triplet biradical, and finally an adduct between the cysteine and the isoalloxazine ring. I think Przemysław showed us some nice pictures of analogous structure of an analogous love domain with this adduct here. So again, we took the evolution-associated spectra, which are very similar to the free FMN. Here's a resonance window. And calculations gives us two transitions within that window, one for triplet, one for singlet. Both of them are charge transfer states from the cysteine to the isoalloxazine pi system. And now we focus a little bit on the low part of the spectrum. Usually it's neglected. People tend to focus on the fingerprint region. And this is the off-resonance of the singlet state. We can see there are many features here, and it's very difficult to assign to experiments. However, if we calculate now the resonance spectra of under this transition, we can see that there is one prominent peak here. For comparison, if we choose another singlet-singlet transition, this is a pi to pi star here, we get a totally different spectrum with another prominent transition. What is this peak here exactly? Is a bending vibration from the cysteine SH bond and out of plane vibration from the isoalloxazine ring here. So this type of vibration can be present both at the S1 state and the T1 state, but its intensity is expected to start to decrease after the formation of the biradical, and especially after the adduct. So we could use this as a marker band for the formation of the adduct. Indeed, in the experimental FSRS, we can see that there are bands, intense bands in the region. However, for the adduct, since unfortunately it's out of resonance, since it's at 390 and our Raman pump is tuned to 800 nanometers, so we cannot get a proper signal to analyze. Nevertheless, the vibrations, I think this slide hopefully shows us the vibrations that are resonance enhanced pertain to the transitions within the resonance window. Yes, so those that are enhanced computationally at least are the ones that pertain to the transition within the resonance window. So I'll move on to the next, to the challenge, which is calculating resonance Raman intensities. Here was from a paper that Andras was also involved. Authors tried to correlate experimental FSRS spectra first with the off-resonance calculations using the B3LYP, which is a very popular functional when calculating FMN structures, both for S1 and the T1 states. Of course, the experimental spectra are taken in resonance conditions. Therefore, they try to also add resonance in the calculations to improve the experiments. However, the opposite thing happened. We have loss, this is the most obvious. We have loss of signal here on the two of the main bands that the off-resonance contain, but not in the resonance calculations. This has led me to embark on a benchmarking study and trying to categorize or see how all these functionals like the B3LYP I showed before, how they perform on computing those resonance Raman intensities. I understand that this is not a very glamorous topic, but I think it's one that is needed for the community in order to get some useful information about which functionals from all the zoo of functionals that exist can be useful, at least for the spectroscopic study. So first we start with, this is the flow chart of the calculations for the benchmarking. We start with the ground state, compute the vertical excitations, optimization of the first excited state, and here's the off-resonance study. You can correlate the off-resonance to the experiment, like in the previous slide, and try to improve it with the application of some scaling factors. I will not go through that part. So this is the off-resonance part, and the resonance part is to, as we saw, how to choose higher excited states and compute the resonance Raman spectra. And finally correlate with the experiments. Of course, since lumiflavin crosses over to the triplet state, you can repeat all this for the triplet, but with an addition of calculating pre-resonance, also calculating pre-resonance Raman spectra. As we saw, the triplet transition experimental is a little bit more moved from the Raman pump in that case. Of course, you can tune your Raman pump to be closer or and therefore more in resonance or not experimentally. But for the given setup, the triplet can be thought as being in a pre-resonance rather than resonance. The first part of the benchmark starts with the computation of the vertical excitations here. I saw 3 functionals. This can be directly compared to the experimental absorption bands of S0 to S1 and S0 to S2. We can calculate the deviation here, and we can compute for all the functionals that are included in that study. The blue and red are the deviations from the experimental value here, while the black line is the absolute average. So they are sorted from worst to best. So we can see that B3LYP is doing quite decently, but even better, for example, is this M06L. And we can also compute them as percent error from observed value to the reference values here. Yes, also shown here. Now we'll move to the main part of the benchmarking, which was carried out by Heba, who came to visit the lab via DAAD scholarship, and Daniel, master student from IBT. Again, we take the experimental spectrum. Here is the evolution-associated spectrum of the first excited state, the equilibrated first excited state, and we calculate the off-resonance spectrum. I chose this functional here, which is a DGA functional, not a hybrid like B3LYP. We see that there are a lot of computed vibrations here, and we can try to do some association between the experimental and computational bands. We see that many bands can be associated to one experimental band, such as here we have these 2 bands to 1570, and the band at 1711 associated to the experimental band at 1626. You expect this, of course, the asymmetric band to be less Raman active than the symmetric stretch. And we can tabulate these results, the experimental values here, the associated calculated peaks here, and their deviation, and do some small statistics. It gives us a 28.3 value for the average deviation, and the percent error is about 1.9. Now we can calculate also the resonance. As we saw, as we've seen before, the S7 was in resonance for this particular level of theory. Can see that there is an improvement in the intensities here. We can calculate again, associate the spectra, and calculate again the deviations and the percent error, which is much better. An advantage of the resonance Raman calculations is that you can associate single peaks now instead of all the peaks in the region. You see intense bands and non-intense, and you can pick exactly which one to associate with the experimental spectrum. As a measure of the improvement, you can also do the subtract these two values. So if it's positive between the off resonance and the resonance, you have an improvement by including resonance Raman intensities. If it's negative, it means that the correlation worsens by including resonance Raman. Here are all the results for the functionals. The gray bars are the average percent errors for each of those, so they are sorted by worst to best, and delta is the difference, yes, positive if the correlation improves with the inclusion of resonance Raman intensities, and negative if it worsens. We can see that for most calculations, inclusion of the resonance Raman intensities improves the correlation. Here are 6 of the best functionals, and with the bars here is the positions of the experimental spectra. We focus particularly on this 1500 reciprocal centimeter region here, and we can see that all these functionals have intense bands in this region as opposed to the B3LYP in the example before. So we managed to obtain like give a set of better functionals at least behaving for the S1 state. We can repeat exactly the same procedure for the triplet state here. Of resonance, we tabulate the results. Resonance, again, we see some improvement of the correlation with the experiment. And also, additionally, we can calculate the pre-resonance spectra. To do that, we have to inspect the experimental transient absorption, evolution-associated spectrum, and see the difference between the experimental triplet-triplet transition and the Raman pump, which is at around 88 nanometers. And from the computed triplet-triplet transitions, let's say we pick the one at 719, we have to add this difference, and it gives us the incident light wavelength. Of course, if we picked a different transition, then we would add that part to that and get a new incident light. So here it is computed. It's slightly worse than the resonance Raman, but still you can see that the line shape approximates the triplet experiment much better. Okay, here are the results. With the gray is with the percent error with the resonance, and with the blue with the pre-resonance. You can see there is a mixed picture, which is the best methodology to approximate the triplet state where you have this triplet-triplet transition in that pre-resonance window. Is still not conclusive. And the final test we can put the functionals on it is how to nuance the spectral shifts we see between singlet and triplet states here. You can see that there are mostly blue shifts when we go from the excited singlet state to the excited triplet state. And for our computed spectra, I chose the resonance Raman for the singlet and the pre-resonance for the triplet. In this case, we capture almost 3 of the shifts, but the other 2 are inversed. How do we nuance these shifts? Where are they coming from? For this particular case, the shift between 1522 in the singlet to the 1533 in the triplet, the blue shift is because of the bond order decrease on most of the bonds involved in that vibration. They are shortening, therefore they contribute to the blue shift of that observed band. So transient absorption is very helpful in the determination of the resonance condition. The Raman pump guides our selection of the resonance states. The vibrational modes that are enhanced are the ones that pertain to the resonance transition, and benchmarking can produce a set of functionals that can simulate accurately the excited singlet and triplet spectra of FMN. And hopefully, these results are transferable to other systems. With that, I would like to thank the collaborators throughout all these years, First Faculty of Medicine for having me, the funding and the resources, and you for your attention.